Welcome to this video in the periodic table unit. This is 4.2, where today we're going to discuss the periodic table. We're going to hit on periods versus groups and talk about the classes of the elements on the periodic table as well as their properties. We're going to talk about how placement of an element on the periodic table will relate to the atom's structure and properties. And we're also going to talk through family names, family facts, and show you some really cool videos that will illustrate reactivity of the different elements. If you haven't already done so, please make sure you have your periodic table handy, you have your chemistry notebook out and ready to take notes, and of course, a writing utensil. So without any further ado, let's get cooking. So let's kick this video off by talking about periods versus groups and the information that is embedded within each. Can't do any of that until we have our periodic table, so pause the video now and grab your periodic table and your pencil and let's get ready to go. So your periods are the horizontal rows of the periodic table, and if you look down at your New York State periodic table, they are numbered 1 through 7, and I could see those numbers that are here. Now you'll notice on the right hand side of your periodic table, I actually don't have any numbers labeled there. It would be helpful for you guys to write those in to help you figure out what period an element is in just at a glance. So what does the number of the period that an element falls into tell us? Well, the period that an element falls into tells us the number of occupied principal energy levels of an atom. Here we can see that with calcium, where we have an electron configuration of 2882, and if we were to count up the electrons, that's what we would get. We'd get 2 here, we would get 8 in this energy level, we would get 8 here, and we would get 2 here. 4 occupied energy levels because it falls in period 4. Let's move on and start to talk about groups. Groups are your colored vertical columns that you see here, and on your New York State periodic table, they are going to be numbered 1 through 18 all the way across the top of the periodic table. You may actually wind up with an older periodic table and see Roman numeral designation. So here's a table that actually has both. You have the New York State designation of 1 through 18, and it's really not just specific from New York State. And then you have what a lot of your advanced placement and your college chemistry books will have, which is your Roman numeral designation. So I wanted to throw it at you so you would see it. It sort of works the same way, and I'll get into a little more about it as we move on later in the video. So let's talk about what's important about groups. The notable info is simply that group members tend to have similar chemical properties, and you may remember that from the video we did on periodic table history. Having similar properties means elements will react similarly with similar types of elements. Now, if you are looking specifically at groups 1 and 2 and 13 through 18, you are going to notice that the members of each group will have the same number of valence electrons. So here is group 1. We'll notice that there is 1 valence electron in each one of those atoms. In group 2, there are 2. Fast forward all the way on the right-hand side of the periodic table to 16, there are 6. And obviously in 17, which is your halogens, there are 7. That is going to mean that these atoms are going to make ions that have similar charges. And we can see that by looking at the oxidation number, which is in the upper right-hand corner of your periodic table box that we see here. Now, why do all the atoms in group 1 make a +1 charge? Well, you guessed it, there's 1 valence electron. And at this point, we know that atoms would like to have 8 valence electrons. And essentially, it is far easier to lose 1 electron, and we'll get into why later, than gain 7. So this lithium atom will have a predictable ionic charge of +1 when it becomes a lithium ion. Move over here to your halogens in group 17, right? There are 7 valence electrons, and we see that the predictable charge is a -1, and that is because it is easier to gain that 1 electron than lose 7. So remember, your common charge is always going to be the first. There may be others in the box, and we'll get into what those mean later, but remember, your first charge is the most common. Here's another graphic that shows the same thing, that as you go down groups 1 and 2 and 13 through 18, you have the same number of valence electrons. And you'll notice that we've left out the transition metals. Well, if you remember back from the atomic theory unit, the number of your valence electrons is variable. So make sure you remember that and are not that guy. If you are doing SPDF electron configurations, just a reminder that your valence electrons are your outermost S and P electrons with the highest principal quantum number that you see. So here, where on your New York State periodic table, it would say you have 3 valence electrons for boron, well, that's because you have 2 that are in your S sublevel and 1 in the P for a total of 3. And you can see that if you were to add up the outermost S and P sublevels, you would get the same number of electrons that the New York State table would get you. Let's now segue into the classes and the properties of the elements. This, guys, is going to be something for you all to memorize. So beginning with metals, you guys probably remember from middle school science these properties. Metals are shiny and hard. They're great conductors of heat and electricity. They are ductile. They are malleable. And for you guys, something new, all the metals that we are going to experience are going to be considered solid at room temperature, with one exception. The mighty mercury, which is a liquid at room temperature. Your metals, and of course we have the metal horns happening here, are all the blue elements. So the majority of the elements that are here on this periodic table are considered metals. While we're on the topic of metals, it's probably important that I bring up alloys. Alloys are not elements. In fact, the alloy is a mixture or a blending of 2 or more metallic elements. And at that point, in order to create an alloy, you have to take those metals, bring them to their melting point, and then mix them. Now, why would people make alloys? Well, one of the reasons that they do it is because the properties of the alloy differ from the original metals that make it up. In most cases, they are shooting for a more desirable property. For instance, many alloys are stronger than the base metal that make them up, or are more heat resistant, or even more attractive. My favorite alloy of all is the samurai sword, which you guys can see here. And it is rumored that the recipe for samurai steel, if we can call it that, is a secret. And samurai swords were known to be far stronger than the swords that the English or the Spanish had. And the reason why, it's rumored that the forge smiths that were making the samurai swords found a meteor and actually used fragments of the meteor to put in when they were smelting the metal, and actually came up with an alloy that had crazy strong properties. I don't really know if this is true, but if you cruise the internet, you might find out more information about it. Finishing up with metals, let's make our way to the non-metals, which make up our second largest class of elements on the periodic table. A lot of the properties of your non-metals are opposite those of your metals. So if you get in a pinch, just go opposite what you remember about your metals. Non-metals tend to be dull and soft. They are poor conductors of heat and electricity. They tend to be brittle and break easily. They are not, as a result of that, ductile or malleable. And what's unique about your non-metals is, as your metals were mostly solid at room temperature, obviously with the mercury exception, your non-metals can be either solids, liquids, or gases. So you can have elements that are each at room temperature, and your only liquid is your bromine. So if I were you and you were me, I would make sure I remember that mercury and bromine are your only liquids on the periodic table at room temperature. And here I have the Kelvin temp, which if I subtract 273, you will get 25 degrees Celsius. So that is your room temperature. The last class of elements we need to talk about are your metalloids. And your metalloids are these elements in yellow here that live on that stairway. And of course, you can't mention stairway without hearing from the wizard, Jimmy Page, who is the lead guitarist and principal songwriter of Led Zeppelin. So metalloids are the elements that you see here in green. And we mentioned that they live on the stairway that's here. There are 6 metalloids that New York State needs you to know. They are your boron, silicon, germanium, arsenic, antimony, and tellurium. There is a 7th, polonium, which you can sometimes see in textbooks, and even astatine. But in terms of what you need to know for a Regents exam and what is expected of you in New York State, there are your 6 metalloids right here. Now, what makes them a metalloid and not quite a metal is that they have properties of both metals and nonmetals. You'll notice that they are on the interface between your nonmetals that are here and your metals that are there. So as we are transitioning, they will have some metallic character and some non-metallic character. Let's talk about what that means. That basically means they're going to have properties of both metals and nonmetals. They are going to be solids that tend to be shiny or dull, kind of like metals and nonmetals. They're going to conduct heat better than nonmetals will, but not quite as well as your metals. So that's why we call some of them semiconductors, and we even call them sometimes semi-metals. They're going to be ductile and malleable, but not quite to the level that metals will be. So make sure you memorize your 6 metalloids and you remember the properties are a blending of both metals and nonmetals. It wouldn't be a video about the periodic table if I did not include your representative elements. Representative elements are essentially your S block and your P block elements. They are groups 1 and 2 and 13 through 18 that we see here in yellow. If you are going old school with the Roman numeral designation, it is your A elements. They are groups 1A, 2A, and then 3A through 8A that you guys can see over here. Now, remember, the notable fact is that if you are doing Roman numeral designation, the number of the group tells you how many valence electrons you have. That might be handy on an SAT2 or an AP. So 11 minutes and 22 seconds in, this is my favorite part of the video. We're going to talk about the chemistry of groups and talk through group names and characteristic properties. You guys are going to need to memorize the name of the following groups, which they will also refer to as families. You'll need to know group 1, the alkali metals, group 2, alkaline earth metals, 13, the boron group, 14, carbon group, 15, nitrogen group, 16, the oxygen group, although they are also known as the chalcogens. Group 17, your halogens, and group 18, your noble gases. So we're going to go through the more notable members of these groups, talk through some of their properties, and tell you what you need to know. Let's start talking about the alkali metals. That is group 1. And the first thing you should realize is there is one conspicuous number of group 1 that is not present, and that is hydrogen. Hydrogen is not an alkali metal. Hydrogen is a gas at room temperature. So if we're talking about alkali metals, we're talking about lithium down to francium. So notable properties of the alkali metals is that they are clay-like metals. Now you may be saying, what does that mean? Well, check this out. Here is sodium, which is a notorious alkali metal, and you'll notice they are able to cut it with a pocket knife. This is iron, which you cannot cut with a pocket knife. So when we say it's clay-like, your alkali metals are soft metals, yet they are still metallic. Take a look at the fact that this does look indeed like a metal. More on that to come. So your alkali metals are the most reactive metals. Now, what does that mean? Well, reactive means a willingness or ability to engage in a chemical reaction, and they are so reactive that they will not exist freely in nature. That means they will always exist combined with something else, usually a halogen. These alkali metals are incredibly reactive, which means they will readily lose electrons. And they all have one valence electron, so it means, as we said before in the video, they will lose that one valence electron and become a +1 ion. Now, one of the unique things that we're going to talk about is the fact that the reactivity of your alkali metals will increase as you proceed down the group. So that means sodium is more reactive than lithium, potassium is more reactive than sodium, rubidium is more reactive than potassium, and cesium and francium are the kings of this particular group. Check this out. We're going to click on this video and watch as they drop lithium, sodium, and potassium into water. You'll notice that the reaction becomes much more vigorous as you start to proceed down this group. So potassium would be most reactive and would react the quickest, and lithium will be least reactive of the whole group. Sodium will be reactive somewhere in the middle. You also want to peep the color of the flame. because this will harken back to talking about the flame test and how the different elements will have indicative colors that they release when they reach an excited state and return to a ground state. So clicking on this video, check us out.
Right, so what can you see straight away as it's doing? So it's starting to fizz and move around there. If it's fizzing, what must be made? Some sort of gas being made in there. So it's really fizzing about. Okay, now we can test the gas if you want to. Right, so look, can you see? So, burning. Go on, let's put yourself out. Right. Wait. Right, so I'm going to put this in then. Ready then? I'm going to put this in. Just make it wet. Right, so there we go. So it's really fizzing. Oh! No way. It's still going, it's fine. Look, there's a little glowing ball there now, look. Yeah. You'll write your observations down, so make sure you see what happens. Right, now, you might have noticed then, I put a much smaller bit.
So that was a pretty neat video, which actually takes 3 of the more safer alkali metals and drops them in water. Make sure you see the observations that we did right here on the left-hand side as the video was going on. It was notable that the lithium took a long time to finish its reaction because it's the least reactive of the alkali metals, whereas sodium was somewhere in the middle with how long it took, and it actually came to a flame quicker than lithium did, but not as quick as potassium, which reacted really quickly and had the indicative violet, sort of peach-colored, sort of potassium flame from the atomic emission spectra. If you guys are playing along at home, you should get on YouTube and do a search for Brainiac. These guys are insane, and they actually do some serious experimentation with alkali metals, including dropping rubidium and cesium into water. So we weren't able to see that in the last video, but they break all the rules and are able to do it. So check that out on YouTube if you can. Now that we're done talking through Group 1, let's get into Group 2, which are your alkaline earth metals. They are really reactive, but less reactive than Group 1 and more reactive than your transition metals. They are still reactive enough that they won't exist freely in nature. They will have to exist combined with some other non-metal. They're not going to do the crazy reaction that alkaline metals will do, but alkaline earth metals will react slowly in water and create hydrogen gas, leaving hydroxide in the water, which turns the water basic. And here I have some phenolphthalein that they put in the water that confirms that with the pink color. Just like alkali metals, your reactivity will increase as we go down a group, which means the reactions will become much more vigorous if you drop, let's say, strontium into water versus, let's say, calcium. They all have 2 valence electrons, as you guys can see here, which means they're going to lose those electrons, revealing an octet underneath. And because they lose 2 electrons, their most common ionic form will be of a +2 ion. Now that we're done with Group 2 and the alkaline earth metals, let's transition further towards the right into Groups 3 through 12, which are your transition metals. These are your metals that have classic metallic properties, and one of the things that you guys are going to find is they are far less reactive than Groups 1 and 2, which means they will still engage in a chemical reaction, but not as vigorously as Group 1 or 2 metals would. They have their classic metallic properties, which tells me that they are hard metals. They are excellent conductors of heat and electricity. Many of them have a high luster and are shiny. And one of the unique things that you guys will find about transition metals is that when you look closely at the boxes on the periodic table, you would see we start to see multiple oxidation numbers that are here. Now, what does that mean? Well, that means that there are multiple ionic forms that these elements can take when they become ions. That is due to the D sublevel starting to fill and overlap all the other sublevels, and electrons start getting taken not only out of the S sublevel, but also out of the D, so they give them some flexibility on how they can create compounds during bonding. Another unique factoid about transition metals is they are known for creating colored crystalline solids and colored aqueous ionic solution. What we say is that they make colored ions. That is an indicator of a transition metal. Here we can see potassium dichromate, and it is the chromium that gives it that unique orangish red color. Iron 3 sulfate is a very nice turquoise. Cobalt 2 chloride is a beautiful color. Copper sulfate and nickel sulfate, these are all examples of colored ions, which are very different than the white powders from groups 1 and 2. You can also see this in aqueous solutions. You can make a rainbow if you really wanted to, if you choose the right metallic salt that you're dissolving in water to make an aqueous solution. So do not forget this. Somebody is going to forget this and wind up being that guy. Don't let it be you. Let's now close this video out by talking about the nonmetals, the names and the nuggets which you guys need to remember. Let's begin with the chalcogens, which we said before is group 16. That is your oxygen group, and you will notice that all of the members in the group are close to an octet, but not that close. They all have 6 valence electrons, and they'll need to gain 2 electrons to reach that octet, which is why, if you look, all of them have the most common ionic charge of a -2, indicating they will pick up 2 valence electrons. Your halogens are next. They are group 17, and what's notable about them is they are the most reactive of all the nonmetals. Fluorine is the most reactive in the group. You will notice that the trend in reactivity is different than the trend in metal reactivity. In a case like this, since fluorine is the boss and is the most reactive, we will see that reactivity will decrease as you make your way down the group. They are pretty close to having a full valence shell. They have 7 valence electrons, and that means they only have to gain 1, which is why the most common ionic charge of a halogen is a -1. Last but not least, we need to talk about the noble gases. If you remember from middle school, noble gases are indeed group 18. It is your helium group, which we see here. Now, what is notable about your noble gases is they don't react with anything. They are unreactive, or here's a vocabulary word for you guys, they are inert. Inert means stable and non-reactive, which is incidentally why they were called noble back in the day, because they didn't interact with the poor people. If you were nobility, right? So how does structure dictate this property of being unreactive, inert, and noble? Well, it has to do with the number of electrons in their valence shell. You will notice that all of the members of group 18 have 8 electrons, which tells me that they have a full valence shell, or if you're playing SPDF at home, they have 8 electrons, 2 in their outermost S and 6 in their outermost P, which fills up those 2 sublevels. That is called the octet rule, which is something that every atom needs to have in order to become stable, and the only exception to the octet rule is the duet rule, which is why helium is in this group. Helium only has 2 valence electrons, but yet it's unreactive. Well, let's go back to atomic structure and remember that in helium, there is only a 1s sublevel, and once you put those 2 electrons in it, that's it. You have filled the energy level, and it is inert. So that is it for me. If you guys have any burning questions on anything that we talked about today, please make sure you bring them to our next session and ask about them. It has been a pleasure taking you through some of the chronicles of the periodic table. We got periodic trends up next. I'll see you on the flip side. Peace out.
That's all, folks.